To better understand what exactly nanotechnology deals with, we need to understand the size. For example, there are various scales for nanoscale even under 1000 nanometers. Nuclear scales such as proton, neutron, electron, quarks and neutrino, we can measure their physically meaning size up to 10 to the minus 15 nanometers. This size is 1/1,000,000th of nanometer. The size of a single atom is typically 1 angstrom, which is equal to 0.1 nanometer. Using quantum mechanics, we can calculate the Broglie wavelength of materials. For example, for the metals, it is about 1 nanometer, while for semiconductors, it is about 10 nanometers. Single DNA has length smaller than 10 nanometers. For example, diameter of DNA double helix is about 2 nanometers, while virus such as coronavirus in nowadays have 10 to 100 nanometers. Most of the man-made nanostructures have sub-100 nanometers targeting nanograding, nanocircuit, nanomotors. However, for visible wavelength, nanostructures can have feature size from 100 to 1000 nanometers, which is equal to 1 micron. In nature, there are many interesting creatures which have natural nanostructures. For example, some butterfly which named Morpho butterfly, has a wing with microscale scales. The scales are composed of several hundreds nanometers wide holes and particles. These hierarchical structure of the wing allows the butterfly to have iridescence, which is also called as structural colors. The structural colors can be found in other creatures such as beetles, birds, fishes, and so on. The structural colors are given by the multiple interference of visible light, which have wavelength ranging from 380 nanometers to 720 nanometers. Therefore, if the nanostructures have the feature size compatible with the visible light wavelength, they can interact with the light, and sometimes, they form photonic band gap, in which light with certain frequency cannot pass through the materials. Why is it important to know about the size of the nanotechnology? It's mainly because nanosize gives peculiar, special, unique, and advanced physical and chemical properties. For example, nanosize can give better catalytic properties based on higher surface-to-volume ratio. It is well known that the surface-to-volume ratio rapidly increases with decreasing the size of the particles. Typical chemical reactions intervened by catalyst occur at the active surface of the catalyst. Therefore, to enhance catalytic reaction, it is important to maintain the surface-to-volume ratio as large as possible. Along with nanoparticles, there are various kinds of nanostructures which can be used as catalyst. For example, you can think of nanoporous membrane or structure. In this structure, pore with size smaller than 100 nanometers are interconnected and form cellular structures. For gaseous phase chemical reaction, this nanoporous structure decorated with some noble metals such as platinum can work as advanced catalyst. One of the famous examples of the nanoporous materials is zeolite, which is composed of nanoporous network of zirconia. Another example is metal organic form, MOF. For nanoscale materials, electric conductivity can be greatly enhanced due to geometric confinement-guided deformation of electronic structures of the materials. In addition, optical or photonic properties can be dramatically varied. For example, in quantum dots with size smaller than 5 nanometers, the electronic bandgap of the semiconductor varies as a function of the radius of the quantum dots. This variation is due mainly to the quantum confinement effects, which are predicted for the materials with features size comparable to Bohr radius. This means that we can control the absorption or transmission spectra of quantum dots with same composition by varying only physical size. For metal nanoparticles with size from 20 nanometer to several hundreds of nanometers, we have already seen some peculiar photonic property of the nanomaterials. This property is plasmonic resonance. In particular, for three-dimensional metal nanoparticles such as gold or silver nanoparticles, surface plasmon resonance can be localized around the nanoparticles, and the localized surface plasmon exhibits distinct peaks in absorption, extinction, spectra. This can be seen in visible spectrum, and therefore, we find different colors from same metal nanoparticles as a function of radius of the nanoparticles. For magnetic properties, nanoscale grain can make superpromagnetism. Nanoscale processed metal alloys or other composite materials can obtain super-enhanced mechanical toughness, ductility, or superelasticity. For example, we can think of nanoporous materials again. In this case, let's think that the cellular materials are composed of graphene nanoflakes. For your information, graphene is two-dimensional carbonaceous nanomaterials. In ideal condition, they form nearly infinite two-dimensional flat monolayer. However, in realistic condition, from typical experimental preparation, we can only obtain graphene nanoflakes dispersed in solution. The graphene nanoflakes solution can be processed with 3D printing, microelectromechanical systems such as microfluidic systems to form designated structures such as closed cellular structures. Due to high mechanical strength of graphene, the nanoporous cellular structure still has good mechanical strength, and thanks to the nanoporous structures, its density is smaller than air. This leads to the development of ultralight ultra-strong materials. The nanoporous and mechanically strong materials can also be applied to develop heat insulator. Due to extremely low thermal conductivity of air, nanoporous structures with air inside can slow down the thermal energy transport across the structures. Finally, for biological applications, nanoscale size allows better permeability of drug materials, higher sensitivity to the receptors, and longer stability of proteins. In recent years, genomics which study genetic information encoded DNA and RNA heavily rely on the sequencing of bases. In past, this sequencing process took so much time and money. However, ever since the development of nanopore, sequencing becomes very accurate, fast, and low-cost process. In nanopore sequencing, different bases go through the nano-size pores of membrane. In the pores, bases exhibit different conductivity, which is directly translated into the position and amount of bases. For therapeutic purposes, metal nanoparticles with relevant size greatly enhance the effects with photothermal effects. As explained earlier, metal nanoparticles with sub-100 nanometers can interact with visible or near-infrared light by forming localized surface plasmon resonance. Due to high extinction coefficient at the resonance wavelength, metal nanoparticles can turn the absorbed photon energy into thermal energy. The thermal energy localized around the metal nanoparticles can give critical damage to nearly tissues such as cancer cells. The quantum mechanical, wave-like, properties of electrons inside matter are influenced by variations on the nanoscale. By nanoscale design of materials, it is possible to vary their micro and macroscopic properties, such as charge capacity, magnetization and melting temperature, without changing their chemical composition. At the nanoscale, the physical, chemical, and biological properties of materials differ in fundamental and valuable ways from the properties of individual atoms and molecules or bulk matter. Nanotechnology research and development are directed toward understanding and creating improved materials, devices, and systems that exploit these new properties. In particular, nanomaterials are defined as any material that has unique or novel properties, due to the nanoscale structuring. These are formed by incorporation or structuring of nanoparticles. They are subdivided into nanocrystals, nanopowders, and nanotubes, a sequence of nanoscale of carbon-60 atoms arranged in a long thin cylindrical structure. Nanoscale components have very high surface-to-volume ratio, making them ideal for use in composite materials, reacting systems, drug delivery, and chemical energy storage. Macroscopic systems made up of nanostructures can have higher density than those made up of microstructures. They can also be better conductors of electricity. This can result in new electronic device concepts, smaller and faster circuits, more sophisticated functions, and greatly reduced power consumption simultaneously by controlling nanostructures' interactions and complexity. Nanotechnology refers to the process, act or ability to work with materials or matter at the scale of 1 to 100 nanometers. The ability of working at this scale renders novel benefits to numerous products and applications such as those found in the semiconductor manufacturing, material science, medicine, and so on. However, what is the size of 1 nanometer? In 1905, German physicist Albert Einstein suggested a mathematical theory on the Brownian motion. In the study, Einstein described the motion of a single particle as a random walk and could derive the relationship between the diffusion coefficient and the size of the particle. Using the theory, he estimated that the size of 1 sugar molecule was equal to 1 nanometer. 1 nanometer would also be equal to the linear size of 10 hydrogen atoms stacked side by side. It is the same as 1 billionth of a meter. A single bacterium is a few hundred nanometers in diameter and a DNA strand is approximately 212 nanometers across. The unaided human eye can see down to about 10,000 nanometers. Human eyes can only detect visible wavelength, and photoreceptors in the human eye are also under diffraction limit of visible light. Therefore, it is not possible for human eye to see sub-10 micrometer feature sizes. Therefore, we cannot see a single cell with few micrometer size with our bare eyes. Here is some diagram for your understanding of size. By our own eye, we can see down to 10 micron. We can see 5 millimeters and 1 millimeters mite, and 50 micrometers human hair. Under this resolutions, there are 7 micrometers red blood cell, 1 micrometer stem cell, microelectromechanically processed modules such microscale motors. Under 1 micron, there are molecules, DNA, viruses, and some small cellular parts such as mitochondria. Most importantly, visible wavelength is in this range, since red is about 700 nanometers and violet is about 380 nanometers. Ultraviolet light has shorter wavelength around 250 to 350 nanometers. Infrared light was longer wavelength than red light, ranging from 750 to 10,000 nanometers. Under 10 nanometers, there are quantum dots, nanotubes, graphene, and single-atom pattern dot. Let's look at the scale on the right figure. You can find different nanoparticles such as fullerene, dendrimer, quantum dot, gold nanoparticles, metal oxide nanoparticles, liposome, polymeric nanoparticles with size ranging from 1 to 100 nanometers. At the same nanoscale, you can also find different biological molecules or materials such as DNA, antibody, oligonucleotide, protein, and viruses. Can you feel the size of the nanoparticles just seeing the diagram? You may not be capable of feeling the size. For your understanding, let us use the Earth and a soccer ball. If we compare the Earth to a soccer ball, we can compare a soccer ball to the full arena. Therefore, a soccer ball is a harmonic mean of the Earth and the full arena. In the lower left corner, you can find an electron microscope image capturing both a human hair and silver nanoire. The nanoires are placed on the surface of the hair. The silver nanowire have 100 nanometers diameter. Can't you still feel the nanometer? Of course you may not. However, interestingly, our own body looks like to be familiar with the nanoscale. For example, human fingernail grows 1 nanometer per second. Man's beard grows 5 nanometers every second. This growth is equivalent to growth rate of 0.5 millimeters per day. Compared with the number of techniques for measuring the size of a particle greater than 1 micron, there are very few techniques that are able to accurately measure the size of small particles, particularly those less than 10 nanometers. For example, atomic force microscope or scanning tunneling microscope can cover from 1 nanometer to 1 micrometer. Nowadays, some specific scanning tunneling microscope or surface-enhanced Raman spectroscopy can see the sub-1 nanometer structures or molecules. Electron microscope such as scanning electron microscope, field-enhanced electron microscope, or tunneling microscope can cover wider range from 1 angstrom to 100 micrometers. Typical optical microscope can cover a range from 1 micrometer to 1 centimeter. There are other methods measuring the size. For example, hydrodynamic size of nanoparticles dispersed in liquid can be measured by dynamic light scattering. Light diffraction can be used to estimate the feature size of nanoscale periodic structures. Although not shown in this diagram, I would like to mention about the scattering method to quantitatively measure the feature size and structural properties of nanomaterials. For example, you can apply small-angle X-ray scattering or neutron scattering to analyze the nanoscale structural properties and feature size of block copolymer thin film and its self-assembled structures. Typically these scattering sources are not available in a lab. Rather, they are available at particle accelerator. In South Korea, we have 3 particle or neutron accelerators. One of the famous scattering sources is located in the southern region of South Korea, in Pohang. However, we need to think about the limitations in the nanotechnology. Every technology has both advantages and disadvantages. The disadvantages also include some issues, problems, and limitations. First of all, for many of nanotechnologies, it is still difficult to make a strong connection to the conventional manufacturing systems. When I had a research project with some company in South Korea a few years ago, we had a plan to develop near-infrared photodetectors based on nanomaterials. My research team had already published several papers in the international journals, and we were confident to develop our materials into commercial products. When we had a research project for the product development based on our nanotechnology, we found that it is much more difficult than expected. The heaviest problems were from the standardization of the basic materials. For example, if you want to use your silver nanoires for the devices in lab scale, you don't need to much worry about the standard. However, for company who would like sell the devices to customer or other companies, every product should be reliable under allowable error rate. This means that the every modules and materials should be under control in the preparation step. Another problem we had met was scaling up. For mass and automatic manufacturing process, company want to have secure and reliable supply of materials. It also wants to expand the production volume to reduce process cost. This was not easy for us, since our team had never considered the volume expansion of the devices. This
Ouais.
prevents nanotechnology from being used more widely for a variety of applications. In terms of safety, many aspects of the nanotechnology are still far behind being safe. In particular, potential toxicity of nanomaterials have been a great burden for the further applications of nanomaterials for healthcare purposes and diagnosis or therapeutics. Compared to active research and development in the realm of nanotechnology, few research on the toxicity of nanomaterials have been done. Once inhaled, nanoparticles stay longer than expected in the body. This is due mainly to the sufficiently small size of nanoparticles. They can easily form some chemical bonding to other biological molecules in the tissue or receptors of cell. They can be easily physisorbed onto the surface of cell or tissue. Some of the inorganic nanoparticles can be turned into carcinogenic materials. Human immune system would recognize the nanomaterials as external toxic particles, and immune cells such as T cells would be much consumed for the response to the particles. This may result in damage to the human immunity. Nanoscale photonic materials such as photothermal gold nanoparticles could be dangerous by giving irreversible damages to the nearly tissues and cells. Once shed by infrared light, gold nanoparticles can absorb much of the photons at specific wavelength, which corresponds to the localized surface plasmonic resonance. If the absorption of the light is too strong, the absorbed photon energy can be turned into thermal energy at 50 or higher degrees of Celsius. In some case, there can be very hot point near the gold nanoparticles. The high-temperature thermal energy can definitely kill the cancer cell. However, it can also definitely kill other cells too. This will give severe damage to the inner body. Some of the nanoparticles and their assembly can be used for bad purposes such as biological weapons for terrorists. Nanoparticles are typically passive. By passive, I mean they can interact with each other or with environment with intrinsic physical and chemical principles. However, it is possible to engineer the particles into the smart nanoparticles. The smart nanoparticles can be implemented with some specific miniaturized modules such as radio frequency transmitter and receiver, thermal sensor, microscale motors, and so on. It is possible to code the smart nanoparticles with only few basic principles, such as stay at least few hundreds of nanometers, recharge the energy when the energy level is under 10%, stay in a long wire shape when squeezed, and so on. Many scientists have already made basic smart nanoparticles. These particles are called active particles. The active particles can be controlled by external stimuli such as thermal gradient, electric field, magnetic field, concentration gradient, physical obstacles, and so on. As was imagined in many Hollywood movies, directed assembly of smart nanoparticles can be troublesome for some purposes. They can attack the building, social infrastructure, and even people. This scenario is not realistic for now. However, in few tens of years, this scenario of nanoparticles under control of terrorists can be very dangerous to community. To advance nanotechnology also make some social and political issues. For example, advanced nanomaterials and devices can be incorporated with advanced systems such as sub-10 nanometers semiconductors or electronics. And there would be limited accessibility to these systems due to limited buying power. Therefore, it is recommended for the researchers to consider possible social impacts of the nanotechnology they want to develop. Now, it is time to talk about perspective of nanotechnology. We have witnessed a transition of nanotechnology from lab scale to industry level. In addition, we also witnessed modification and convergence of nanotechnology with other conventional or newly emerging technologies. The tendency of the integration of nanotechnology with other technologies will be further enhanced in future. The convergence is inevitable since technological demand for the advanced systems and devices will be ever increasing as time goes by. For example, in this course we are dealing with the nanotechnology, information technology, and human-computer interface, and their convergence. In terms of nanotechnology, information technology convergence, what can you think of? How about touch panel of smartphone you are using every day? The touch panel is basically from materials science on the nanoscale piezoelectric materials. How about optical communications? For the optical fibers with broadband optical signals for your wireless internet systems, nanophysics and nano-optics have been intensively employed to design photonic crystal-based optical fiber. For example, nanophotonics will actively use nanotechnology to design nanoscale photonic devices such nanolaser, nanodetector, nanoantennae, and so on. Using these basic modules, nanophotonics will pursue to be integrated with silicon photonics and silicon electronics. In terms of nanotechnology human-computer interface, what can you think of? For the computer vision, it is important to build an advanced vision system which is similar to human eyes. For this, artificial retina or photoreceptor can be implemented with CMOS or CCD sensors. Therefore, it is mandatory for the nanotechnology to make a strong convergence with other technologies. For better and higher added values and to meet the ever-growing demand for the advanced systems. As time goes by, nanotechnologies will work as a hub to accommodate other principles to expand its realm. We also expect that nanotechnology will keep growing ever. For example, total world market containing nanotechnology will hit $1,000 to $10,000 billion by 2030. Economists predict that nanotechnology will accelerate the growth rate of every manufacturing sectors by providing basic building blocks and modules. Due to this reason, many developed countries have invested their resources into the fundamental and application research projects for universities and research institutes and companies. For detailed market share, let's look at this table. Sorry for the Korean. There was big growth between year 2000 and 2010 with 25% average growth rate. However, the growth would be doubled between year 2010 and 2020. The largest market of nanotechnology would be the United States. However, by year 2030, the largest market could be China and India. This depends on the GDP growth rate of the two countries. By year 2030, total amount of sales concerning nanotechnology will hit $30,000 billion. This is about 10 times greater than that is expected in 2020. Annual growth rate will be more than 40% by average. Have you ever wondered why the nanotechnology market is so big? This is mainly because of the fact that majority of the market is B2B. This means that typical consumers would not feel the real portion of the nanotechnology. Most of the products from the nanotechnology are intermediates such as modules, processes, materials, composites, films, chemicals, and so on. These intermediates are not directly available to most of the consumers. However, just because consumers are not familiar with nanotechnology products does not necessarily mean the market of nanotechnology is small.